Hi, welcome to a brand new section of this course, Using Force. We'll start off this section with using gravity and charge and customizing velocity. Then, we will move on to setting the link constraint and using force to assist visualization. Lastly, we'll take a look at building a force-directed graph. Let's start with the first video of this section that deals with using gravity and charge. In this video, we will learn how gravity and charge can be leveraged to generate various effects with a particle system. One objective of force layout's design is to loosely simulate the motion of particles, and one major feature of this simulation is the force of charge. Additionally, force simulation also implements pseudo-gravity, or more accurately, a weak geometric constraint typically centered on the canvas that can be leveraged to keep your visualization from escaping the canvas. Let's see how these two fundamental, sometimes opposing forces generate various effects. Open your local copy of the gravity and charge file. In this code, we experiment with the force simulating gravity and charge settings so you can better understand different opposing forces involved and their interaction. This code generates a force-enabled particle system that is capable of operating in these modes. Now, before we get our hands dirty with the code example, let's first dig a little bit deeper into the fundamental concepts of alpha decay, velocity decay, charge, positioning, and collision so we can have an easier time understanding all the magic number settings. Alpha determines how hot a simulation is. A simulation starts with alpha of 1 and decay towards 0 by default over 300 iterations. Therefore, if you set the alpha decay to 0, meaning there is no decay, therefore simulation will never stop. This is the setting we use in order to better demonstrate the effects. At each tick of the simulation particle, velocity is scaled down by a specified decay. Thus, a value of 1 corresponds to a frictionless environment, whereas a value of 0 freezes all particles in place since they lose their velocity immediately. Charge is specified to simulate mutual n-body forces among the particles. A negative value will result in mutual node repulsion, whereas a positive value will result in a mutual node attraction. If X or Y positioning forces are specified, the simulation will push particles toward a desired position along a given dimension with configured strength. This is typically used as a global force that applies to all particles in the simulation. The collision force treats particles as circles with a certain radius instead of sizeless points. This will prevent particles from overlapping in a simulation. Now, with the dry definition behind us, let's take a look at how these interesting visual effects are generated. To set up zero force layout, we simply set up force layout with neither gravity nor charge. The force layout can be created using the D3 force simulation function. First of all, we disable alpha decay so that simulation will continue to run without cooling down while setting the velocity decay to 0.8 to simulate the effect of friction. Next, we set the collision to slightly larger than the radius of the SVG circle element we will create later. With this setting in place, we then create additional nodes represented as SVG circle on SVG whenever the user moves the mouse. Node object is created initially on line A with its coordinates set to the current mouse location. Like all other D3 layouts, force simulation is not aware and has no visual elements. Therefore, every node we create needs to be added to the layout's nodes array on line C and removed when the visual representation of these nodes was removed on line B. By default, force simulation starts automatically as soon as the simulation was created. With zero gravity and charge, this setting essentially lets us place a string of nodes with our mouse movement like this. Moving on to setting up mutual repulsion. Now, we set the charge to a negative value without any global positioning force in order to generate a mutual repulsive force field. These lines tell force layout to apply -10 charge on each node and update the node's XY coordinate accordingly based on the simulation result on each tick. However, only doing this is still not enough to move the particles on SVG since the layout has no knowledge of the visual elements. So we need to connect the data that is being manipulated by force layout to our graphical elements. This is the code to do that. Here, we register a tick event listener function that updates all circle elements to its new position based on the force layout's calculation. Tick listener is triggered on each tick of the simulation. At each tick, we set the CX and CY attributes to be the X and Y values on D. This is because we have already bound the node object as datum to these circle elements. Therefore, they already contain the new coordinates calculated by force layout. This establishes force layout's control over all the particles. Other than tick, force layout also supports some other events. Tick, triggered on each tick of the simulation. End, triggered when a simulation ends. Now, the force setting generates this visual effect. Let's now set up gravity. When we change the charge to a positive value, it generates mutual attraction or gravity among the particles. This code generates a visual effect like this. Next, we set up positioning with gravity. When we turn on gravity with central positioning force, then it generates a somewhat similar effect as the mutual attraction. However, you can notice the strong gravitational pull as the mouse cursor moves away from the center. The code generates this effect. Finally, we can turn on both positioning and mutual repulsion. The result is an equilibrium of forces that keeps all particles somewhat stable, neither escaping nor colliding with each other. Here's what force equilibrium looks like. Isn't it amazing? You can refer to velocity virlet integration at this wiki link. For more information on scalable, versatile, and simple constrained graph layout, visit this link. And yes, for more details on D3 Force Simulation API, visit this GitHub link.